So today's talk, we're going to look at the reader monad. We probably will look at a generalization of the reader monad if we get to it, and maybe one other topic. So I want to get started. We're going to use a similar project setup we've been using for the last 2 weeks. So we've got structures on the class path. We have simulacrum. We have kind projector, compiler plugin, and macro paradise so that we can use simulacrum. And otherwise, it's an empty project. So I want to get started and just look at the basic reader monad first. So we're going to create a case class just like we did with option T and either T. We're going to parameterize it with two type parameters. And basically, the reader monad is just going to abstract over or wrap a regular function. So we'll start writing it like this. Now I'm actually going to change the name of f, because typically we use f to represent a function argument to a method, like map or flat map or something. So I'm going to change this. I'm going to change it to the word run. But it's just, this run name here, it's just a regular case class accessor for, a function from A to B. And now what I want to do is start defining instances and methods for things like, instances for things like functor and monad, and methods like map and flat map directly on our reader case class. So let's just start with a simple definition of map. Now map, we're going to have to pick a type parameter that doesn't shadow either A or B. So we'll define map to take type parameter C. And we'll take a function. And we're going to take, we have to decide what the input type to this function is going to be and what the output type is going to be. Normally, if we were working on, I don't know, with a list, let's say, maybe we would write map something like function from A to B is going to return a list of B. Up here, and notice by the way that the type parameter to map was the output of our function, and we returned a list with that output type parameter here. And this A, the input to our function here was fixed, right? It was fixed by the fact that we were defining this map on a list of A. So up here, when we define the map function for reader, we have to decide, where C is going to show up. So let's say that it shows up on the output side of our function. We're going to return a reader. And so anyway, we have to decide both what the input here is going to be, as well as what the output to type parameters of reader are going to be. And what I want to do is make our map function operate on the B type, on the the right-hand side, just like we wrote either, for instance. So if we go through and apply the pattern, what that means here is that this is going to be B to C. It means the output here is going to be C. And we're left with this parameter we're not sure what to do with, but just like with either, when we mapped the function from B to C over either, we mapped it over the right, we left the left side alone, right? We got back an either AC. And so with reader here, we'll have the same pattern. We're going to leave the left side of the function definition alone, leaving us with a reader AC. So to implement this function, we're going to just use the reader constructor. This is a case class, right? So we've got the normal apply method. And now we need to pass a function from A to C. And that's pretty trivial to implement. We have a function from A to B, and we have a function from B to C. So this is just regular function composition. We could write it run and then f. Let's do the same thing with flat map. Now that we know that we're operating on the right side, or we're operating on the second type parameter, we can write this a little quicker. We're going to have this function f, the input will be b again, and we know we're going to return a reader a comma c, and overall we're going to get back a reader a comma c. Because we are returning a reader AC, what we're putting here, we're going to use the, we're forced here to use the reader constructor. At least as of right now, it's the only way we have to create an instance of reader. This time, I'm just going to declare it anonymously, or just to declare this callback here. We get the a parameter as an argument. And so now we've got both run and we've got this function f, b to reader ac. So we can try to put the pieces together. We could call run, or apply this input value a to run. This is going to give us back a value of type b. And then we could apply that value of type b to f. This will give us a reader ac. Now, this isn't quite good enough. If we just try to return R here, what we'd end up with overall is a reader A, reader AC. So we have to somehow unwrap that. So let's take a look at what we have. Since R is a reader AC, that means we could do r.run to get a function from A to C. And if we have a function from A to C, we can lift any function from A to C into a reader AC just by using the apply method of the reader case class. So this should compile. This should be what we want. Let's see if we made some mistakes here. We have a syntax issue there. Oh, no, that's not quite what we want. We would have to, let's think, we'd have to apply this run here. So the issue here is that we're returning an AC here, a function from A to C. But we're inside this function here that was a function from A to whatever the result is. So what we have overall here is really a reader A to C. Now the compiler knows that we're supposed to be returning this because we annotated our type here on flatmap, and that's what it's complaining about, is saying, well, wait a minute, this inside of this expression here was supposed to be returning a C, and you're really returning a function from A to C. Okay, so we have an A. Right, we have this input value A that's still sticking around from earlier, so we can apply that A to this run function to get a C as output. And then we could just return that C. So this will compile, and then we can do a little bit of code cleanup. So for starters, let's just get rid of this C value. We'll just inline the run expression. And then let's also inline this R expression. And finally, if we wanted to be a little bit shorter, we could write it like this. Let's go ahead and write one more method for reader, and then we'll actually try to use this for something. So I'm going to, in the companion for reader, I want to define a constructor. We already have one constructor that lets us lift a function from A to B. I want to define another constructor that takes no arguments, but gives us an instance of a reader nonetheless. So I'm going to call this function ask. So it's going to have a single type parameter A, and it's going to be a reader that fixes both the input and the output type to the same value A. And all we're going to define this as is reader of identity. the identity function, of course, whatever we pass to it, it returns. And this definition here is kind of interesting. We'll see why in a few minutes. But let's start trying to use some of these things at, let's say, the REPL. Okay, so now that we're at the REPL, let's define a few functions that operate with reader. The first thing I want to do is define an alias for reader that fixes our input type to be a specific value or a specific type. So we're going to define like string reader as an alias for reader where our input is fixed to string and our output type varies. So let's say the first thing we do, let's say we have something that reverses a string, and we'll have another function that like uppercases a string. So the first one will be called reverse. So here we've defined rev to be string reader of type string, and we're using the apply method on the case class. The compiler knows that str is of type string because we annotated it on the left side over here. It knows the input string because of the type alias of string reader. It knows the output string because of the type annotation right here. We'll do the uppercase example as well. And now let's try to combine these two functions into another function, or compose these two functions such that we don't have to manually feed our input string to both of them. So what we want to do here is come up with some way to effectively compose these together without manually threading our input value through them. So our only two combinators we have right now are map and flat map. We could use map and let's start with that. We could use map to operate specifically on one of these two. We can't combine them quite yet with map, but with one of these two, we could say like rev map in this case, we're mapping the to uppercase method over the reverse reader. Of course, we still have a reader type as a result. We haven't changed the input or the output types. And so whenever we're ready to run this, we could say res0 dot run and pass in a string like hello. In this particular case, we have fused together our reverse behavior that we started with and the results of an individual, to uppercase function, and we were able to fuse those together without operating on an input value yet, and then apply an input value later. So of course we could, use res0 again with like a different string, and get the same behavior again of both, reversing and then uppercasing. And we could do the same thing with our up reader. So this case, up is already going to, or up's going to give us uppercase. So let's say we'll map the reverse function over it. We could say res3.run hello and res3.run world and get the same effect. We don't quite have a way to put these two together directly yet. So of course we could do something like rev map up.run, right? We could unwrap the second reader. Just throw away the fact that it's a reader, get back the original function and map our function over it. But we don't have a way to combine them directly. So we're going to look at another combinator that lets us do that. Another thing we can do, though, because we have flat map defined, we can now, and map, we can use these in for comprehensions. So let's start like this. Actually, let's call this message. We'll start with a reader that is just the result of calling our ask constructor. And we're going to ask for a string. And so this turns into just a regular reader string comma string because of our definition of ask here. And then we're going to call flat map, which makes message here our output type, and it's going to be bound to whatever was input to us. And now we could do, let's say, rev message. And we can just yield that as a result. And notice, the result we get here is still a reader string comma string. And so if we actually wanted to apply this with a value, we could say run with hello. So in this particular case, we were able to use this ask combinator to get access to our input string value without ever having to write a callback function directly. So what's the point of wrapping functions in this reader monad? The key idea here is the way flat map lets us ignore the fact that A exists. That's the key effect that reader is going to be providing us. Like when we were writing this for comprehension, we didn't ever have to think about the fact that we were dealing with this threading or this access of this input parameter to various generators throughout the for comprehension. When we wrote the definition of flat map, we handled that threading automatically. Right? We said, given this input value A, thread it into both our own run method as well as the run method of whatever resulting value came back from applying F. And so this notion of abstracting out the input to the function lets us write programs in for comprehensions that abstract over dependencies on values. So what I mean by that is we could write something like this. We could have a trait let's say we have some trait that represents like a user service to get some user account or something. In fact, let's make it, well, that's fine. Let's just leave it like that. Rather than writing a series of functions that all need access to the user service, rather than writing all of those such that you have to manually pass the user service to each one of them, we can abstract over that dependency. So for example, we could write one function like this. We'll write one called getLastLogin. And maybe we return some like long representing a date time or something. The getLastLogin method needs access to a user service here. So one way to do it would be passing it as an explicit parameter to this method. And then inside of this function, we would do something with the user service, perhaps something like that, right? I'm not going to go through the work to make that compile right now. But the idea here is just that we're expressing our dependency on the user service as a parameter to this function. So if you imagine that's what that function's doing, then instead of writing it like this, and actually, let's write one more. We'll say a function called getRoles that takes the user service and a username, returning like a list of roles. We'll just define those as strings for now. So of course, if you needed to put these two pieces together into a larger program, your only real option would be to manually thread that user service through everything. So for example, you might do something like this. If we call getLastLogin, we can pass name and user service. And then we'll call getRoles. And for now, we can just like return these two things in a tuple or something. And so what we're going to try to do with this reader monad, even though it's only a wrapper for this function from A to B, we're going to try to use it to organize code that looks like this in a little bit easier way. And we're going to abstract that. We're going to pull this user service parameter out of each of these functions and make it the input type to our various functions we're wrapping with reader. So let's write each of these again, but this time using the reader monad. We're going to remove the user service from the parameter list, and instead move it into the, or we're going to change the result type and move the user list into the input to reader. And then our output type will be the original return type of this particular function. So using that transformation, getLastLogin ends up returning a reader of user service come along. And now to implement this, we have a bunch of different ways. One way to do it is to use ask. So we would say for US in reader.ask for a user service. And then we could say like yield, user service, maybe .getLastLogin of username. Another way to do it would just be to create it directly with the apply method, in which case we're just pass the user service directly here, and then we could do the same code that we had in the yield we could put here. So for now, I'm going to leave it like that, and we're just going to hard code a 0, just like we did before. GetRoles would look very similar, but this time our output type will be a list of string. And then finally, let's see what get login info looks like. Here we were just returning a tuple. So we are overall now returning a reader service, input is user service, and our output is our tuple type. Here we'll use our for comprehension and say last is get roles of user. Oh, sorry, is get last login of user. And roles is get roles of user. And overall, we'll yield just last comma roles. Oh, that was name. I'm sorry. Okay. So notice in this definition of get login info, we didn't have to thread our user service through all of our methods. We were able to do that automatically using the for comprehension. And inside this for comprehension, we stayed within the reader data types. Right? Get last login is a reader data type. Get roles is a reader data type. So we never even had to talk about user service because this entire method body was in terms of reader. So of course, if we were to call get login info, then we get back a reader, and then we actually have to run the reader with a given user service. If we just call run, we get back our unwrapped function. And you can see we have now composed this function up. We've built a function gradually that, given a user service, will give us back our tuple long and list of string. And so this is the general idea of reader, the idea that we can abstract out a dependency or an environment, this A parameter. We can abstract over it and compose various readers that share the same input type via map, via flat map, and via a couple additional operators that we can define. Let's define one of those additional operators. We'll just define and then to mirror the function syntax. Right? So if we have a function from A to B and a function from B to C, we used and then to get back a function from A to C. Let's do the same thing using readers themselves. So if you have a reader AB and you call and then on it with a reader BC, I'm sorry, a reader AC. I'm sorry, no, that was right, BC. Then we can give you a reader AC. And this is just pure syntax for unwrapping this and that, and then rewrapping, composing them and rewrapping in reader. So what I mean by that is that here we're going to unwrap this using run. And then we will use that.run. We'll unwrap that, combine them together, and rewrap with reader. We can do the same thing for compose. Compose is just like and then, but it's in reverse. So basically what we want to do is say that dot, well, we could say that dot run and then this dot run. We're going to get a slightly different type, right? If we do it this way, that dot run and then run, think what that means. We're taking the output of the parameter that's coming into us and feeding it to the input to our run, which means the output here must be type A. And then C would have to be our input type. C is our new type parameter. And then what we would get back overall would be C to B. Oops. So let's look at a quick example of that. Here we'll just do our uppercase example again. Let's say we have another one that takes a length of the string. And maybe we'll have an increment. Whoops. Okay. So we can use and then to go from a string int to an int. So for example, to put those together, we might say len and then inc. We get back a reader string int. And if we did like res0.run of hello, we should get 6, right? One more than the length. We could do the opposite where we say like up and then length. Kind of silly, right? Because uppercasing a string is not going to change its length, but nonetheless, we could combine them that way. Run it. And get the right value. And if you work through the definition of compose that we did, it's really just and then with the parameters reversed. So any of these examples we just did, like up and then len, we could write instead as len compose up. Or like our length one, where we did len and then inc, we could do inc compose len. And to show you that it does in fact do the same thing, we should get 6 again when we run that. Okay, so with and then and compose, we can now compose readers in the same way that we compose functions. That's really more convenience, though. The real key here is the fact that we can flat map these things together. All right. Let's define just the monad instance, because I wanted to move on to the more general definition of reader in a second. So we're just going to write a monad definition here. We could start and say, like, all right, we want to define our monad instance as an implicit val. We want to define it of type monad reader, and then we have to pick a type to vary over. So this is the same exact pattern we used with ReaderT, where we got this far, realized we need to fix the left parameter and let it vary over the right parameter. And so we use kind projector syntax to do that, but then we need to switch this to an implicit def and take this A type as a type parameter here. Okay. We need some imports in order to define the monad instance. We're going to need structures, and it's going to complain and tell us what methods we need. So let's take these two definitions and put them here. So pure, let's implement pure. Pure says for all a, given a value of a, we need to return a reader of a comma a. Now the compiler figured that out, right? The compiler was able to, well, this is this is not quite accurate. This is a bad name replaced by the compiler. I'll show you what I mean. Let's just leave that undefined for a moment. We'll clean up the flat map signature. And I'm going to compile this and show you the error we get. All right. So we get two, well, in this case, they're warnings, but I have fatal warnings turned on. So they turn into errors saying that our type parameter shadows, our type parameter in both pure and flat map shadows the type parameter a defined up here. Up on, the type parameter on line 24. So let's just change this one. I'm going to change it to R. And now what that's going to do is everywhere we have this reader type, everywhere the left parameter shows up, that's going to turn into an R. And now we're compiling again. And the bug there is that when the compiler auto-generated the code for us, it defined this name here A, but it didn't notice that that name was already used up here, and then it gave us this very confusing data type here that had A and A, even though one of these was referring to this shadowed one, and the other one was referring to this one, which of course is not legal. Okay, now that we've gotten rid of our name clash, though, we need to implement pure. And pure is interesting. Pure just says that you have a value, some value here, A, that's not dependent at all on your environment, R, on your input parameter, R. So we can implement this very easily with like the constant function. Given some value R here, we're just going to ignore it completely and return A. And flat map we've already implemented. So we can implement that just by calling our flat map method. And there's our monad instance for reader. So of course, because we have a monad instance for reader, we can use it, like with the either-t monad transformer we looked at last week, or we could use it with option t, or any of the other things that require monads that we've looked at. All right, but I want to look at a generalization of reader. So let's start a new project. I want to look at ReaderT, the transformer version of reader. All right, so ReaderT, just like the other transformers we've looked at, it's going to let us combine this ability to abstract over an environment with the effect of some other arbitrary type constructor. So we're going to need the type constructor as a type parameter, and we'll just do that in the same way we did it with like option t. And the way we're going to kind of fit this ability or this effect f into our signature here is that we're going to abstract over functions of the shape a to f of b. So like if you had a function that went from string to list of int, that would fit this shape, right? We would just say that our type constructor f would be list and b would be int. So let's try a couple different things here. Let's try implementing map. We can't use the same definition we used before. Our run method here is going to return an f of b. We have a function from b to c, so we have a bit of a problem. We can't just call and then because that is only going to work if the output of run matched the input of f, and they clearly are different. So we need some other approach here. So let's use our callback approach to define this ReaderT. We'll call the apply method. We get this input value a. Given our input value a, we can apply it to our wrapped function, and now what we get back is an FB. Right, and we'll look at this exactly in the same way we derived flat map for reader. So, okay, so we start with this. We have an FB now. What we need to return here overall, note, is an FC. So our goal here is to get to an FC. And of course, this is an FB. Now we have a function from B to C. So given the fact that we have an FB and we have a function from B to C, it looks like we just need map here. So if we could just do FB map F, we have everything we need. That'll give us an FC, and then our ReaderT constructor will be happy. So if we inline our FB, what we really have is run A map F. But how can we call map on this arbitrary type constructor F? There's no way to do so given what we've written so far. What we could do instead, though, just like when we were implementing map for option T, is that we could ask for the minimum type class that captures the ability we need in this function. So we'll take an implicit parameter to map, which is going to be a functor instance for our F type constructor. And then we can just say f.map. Just syntax-wise, we're going if you recall, the functor type took the value to map over in its first argument list and the function to map with in the second argument list. Okay, so let's see what's, oh, and the only thing left that's wrong is I forgot to change the return type here to be ReaderT FAC. Right, because when we map over ReaderT, we want a ReaderT back, right? Map, we're not allowed to change the overall type we're working with. All right, so there's our working definition of map for ReaderT. Let's do flat map. This time we'll try to get it right the first time. So we're going to take a ReaderT, or the function that we get is going to be a function from B to ReaderT FAC. And that means we're going to have to return a ReaderT FAC. That should compile fine. And now we'll add an implementation for it. All right, so let's try to do it in the same way we did it before. First, we called run. This is going to give us now an FB instead of F. We have an FB, and we have this F that needs a B. If we were to try to do the map trick we just did, what do we end up with here? Our type ends up being F of the result of our function F, which is going to be ReaderT, F, A, and C. What if instead I'm just going to expand this out into full syntax for a moment. So rather than just passing F as a higher order function directly to map, let's instead pass a closure where we just immediately apply F with B, right? So that has the exact same type, of course. That doesn't change anything. It's just different syntax for the same thing. So now that we've done that, what if we refactor this body of this closure here to unwrap our ReaderT? Right, because the result of FB is going to be, this is a ReaderT FAC. So what if we just unwrap that? We can unwrap that via run. So what do we get as a result? We're still going to have B and F, right, because we're just mapping over a functor. So we're still going to be in F. but now we're replacing this ReaderT FAC with a function a to f of c. But now this looks a little more promising because we have an a. Here's our a value up here. So we could apply that inside our map. If we did that, right, we're just going to say apply a here. That changes the output here. We're just going to move the a out. Now we have an FFC. And anytime we have an FF, right, we can combine those two F's into a single F via join, right? So of course, like if we had like, I don't know, like list int, using our monadic join method, right, we could just join these two lists into a single list. Right, we would say like xxx.join, assuming we have got a monad for list, and we do. But we don't really need to join in this case because we're mapping. And if we look, or if we think about what we're doing, we have an FB, and what we're converting each individual B into an FC, right? So we started with an FB, and then we said for each B in our F, convert it to an FC, and that's what's given us this FFC. So like anytime we've got this pattern of like FA, and we're going to map some function from like A to FB, and hence what we get back here is now FFB. And then all we're going to do immediately is like join these, or using the standard library, we would call this flatten, to get back an FB. Right? Anytime we have this particular pattern, like map and flatten, we can just combine it into flat map with the same exact function, and we still get an FB. And these two are exactly identical. So what we're really saying up here is rather than mapping over FB, we just want to flat map over FB. If we do that, we get rid of this type constructor, and we are left with an FC. So now we have a callback that's taking A as input and returning an FC. And that's exactly what we were trying to get. Whoops. That's exactly what we were trying to get with our ReaderT signature here, because we were returning a ReaderT FAC, and if we plug FAC into our pattern, we get A is our input type, F is the same, but we're going to replace B with C here, so that's exactly what we wanted. So our implementation for a flat map looks like that. Now, we can't just call flat map because we don't have, we haven't defined our constraint yet. So we're going to add that as an implicit parameter here. And I mean, we haven't looked at the flat map type constructor yet. So really maybe, since we've only looked at monad, we can replace that with monad. All right, so let's compare the definition of flat map for ReaderT compared with the one for reader. Both of them, we wrote callback style. Both of them took this A as input. Let's inline this FB for a minute. So we're just going to inline it right here. And so they both took this input A. They both called run A immediately. But in the reader version, we were able to take the result of that and apply it directly to F. Whereas in the in the ReaderT version, we needed to defer that application until we were inside our flat map call. Right? We weren't able to apply it until over here. Whereas down here, we were able to apply it directly to the result. And that's the only difference, right? Because then once we're done there, we immediately called run A in in both cases, run A and run A. So the only difference between reader and ReaderT for flat map is the fact that when we go to work with the return of our function, we need to do it inside this nested call to flat map. All right, real quick, let's implement and then and compose. We're gonna have a similar problem, right? Where we can't use let's type it all out. So and then we're gonna let f be the same. We're gonna require f to be the same in both this and that. But otherwise, we're going to have the other two type parameters match the same pattern as before. We're going to use the callback style again, or closure style again. So we're going to create a new ReaderT that takes A as input. We can immediately apply that to our run value. That's going to give us an FB. We need to use that.run. And we know that.run is a B to FC. And so you can guess that in order to get in there, to get access to it, we're going to have to use either a map on flat or map or flat map on FB. And since we know we're going to get an FC back, we might as well just go right to flat map this time. And apply that.run with B. And we'll inline our FB. And that should be our definition of and then. We're going to need our implicit here. And I forgot the T right there. All right, so there's our definition of and run. And I want to implement compose even faster. For compose, let's fix our type signature first. We're going to require a ReaderT FCA, and we're going to return a ReaderT FCB. And I'm just going to implement compose in terms of and then. We're going to say that and then this. We could have done that earlier as well, by the way, in the reader version. In order to call and then, we need an implicit parameter. That's what the compiler error is about. So we'll steal the one from and then and put it right here. All right, so we have and then and compose now implemented as well. We can now implement ask. Ask is a little more interesting. Let's inline our identity function here, right? Identity function looks like that. Ask, we're going to need an additional type parameter, right? We're going to have to take this f type parameter. But otherwise, it looks mostly the same. But the problem here with our identity function is that it's not the right shape. A ReaderT FAA, the shape of function that it wraps is A to F of A. But we're giving it an A to A. So we've got to fix that. In order to fix that, we need to somehow take this input value A and lift it directly into F, the type constructor F. So how can we go from an A to an F of A? The only method we have that does that is pure from applicative. So here, we're going to require an implicit applicative for F, such that over here, we can write f.pure A. So there's our definition of ask. And finally, we can implement monad for ReaderT. This is also a little more complicated. So we're going to define the type constructor F as a type parameter to our method. We're going to replace all uses of reader with ReaderT. And we're going to insert that type parameter F in each individual use. Flat map should be easy. We've already implemented it. We can just call it. Pure should be easy as well, but we're going to have to play a similar kind of trick we just played with ask. So let's look at that. Sure enough, that's the first error we get. It says you're returning an A, but you're supposed to be returning an F of A. So we can't add an implicit constraint to the pure method or the flat map method. Just like when we did the other transformers, constraints on the instances we had to put up at the constructor level of the instance. So we'll do that here. We're going to need an applicative for F in order to say f.pure A. The next compilation error is flat map, where it complains that, well, a couple of things. One is I forgot the F here. But now it's going to complain about how the flat map method that we're calling up above requires an implicit monad for F. And so we could add, a monad constraint here. But since every monad's also an applicative, we could just change this to be requiring a monad for F. And now you can see it compiles. So this is neat. This is what we've said, is that you can take any old monad F, it doesn't matter what kind of monad it is, and fuse it with ReaderT, and you get back another monad. Okay, so for the very last topic with ReaderT, it turns out we don't need reader at all. So let's get rid of it. What we're going to do, I'm going to define a new package object. And we're going to do a couple things. The first thing I want to do is define a new data type. We're going to define a type alias. We're going to call it ID. And it's going to be parameterized on a single type parameter A. Right, so this is just like saying, type foo sub A equals like list of A, right? Here we're aliasing foo for list. So what I want to do is alias ID of A to be equal to A. The next thing I want to do is define a companion object for this ID type. So it's a companion object for this type alias. And I want to define an ID monad. Now, in order to do this, I'm going to have to import structures just to get the definition of monad. Whoops. All right, so we're going to need two methods here is what the compiler is telling us. We have pure of A, and we have to return an ID of A. So let's think about that for a moment. Let's also write down the flat map signature. Okay, so here's what we need to implement. Like this should compile at this point, right? Oh, not quite, because I had a syntax error. All right, this will compile at this point. Now we just have to implement, pure and flat map for this new strange type called ID. So ID is just a type alias for its type parameter. So an A really just is an ID of A, right? They're the same thing. Like, this is not a case class that wraps it, right? There's no runtime overhead to this. It's purely just an alias. So we can implement pure just by returning whatever value is given to us. And that compiled fine. We can implement flat map in a kind of a similar way, right? We've got a function A to ID of B, we need to return an ID of B. All we have is an ID of A, but since ID of A really just is an A, then this is just regular old function application. And there's our monad instance for ID. So this is really neat, right? What we just did is said that any value in the world, not type constructor, but any value, like any single proper type, has a monad instance just by lifting it into the ID type constructor. And that lift is only happening at compile time. We're not lifting it into a type constructor at like runtime, right? This is not a wrapper. This is not a case class. This is purely a type level computation. There's nothing at runtime. Okay, so given this kind of wacky data type, actually, let's make sure we got it right. Let's go to the REPL. And let's import explorations. Oh, I spelled the package object wrong, so that's going to be the first problem. All right, so given this, what we should be able to do now is to say like x is going to be equal to ID of int. And we'll just make it 1, right? That worked okay. We can say like f maybe is int to ID of int, and we'll just make this like increment, right? And that works fine. And then we can do something strange. We can say using the monad for ID, we can flat map x with f. And we get back 2. 1 plus 2, right? So this is letting us treat like just an integer as a monad. And there is no effect we're capturing here, right? Like the identity monad is one that has no effect. It purely lets us treat proper types as monads. Okay, so why do we care? Why would we ever define this weird thing called ID? Well, we can delete reader now. Let's just comment out this entire, well, let's comment out this entire data type, the whole case class. And then what I want to do is I want to define another type alias. We're going to say a reader of AB is really just a ReaderT of ID AB. So our type constructor that we're going to use with our transformer is just the identity type constructor, this ID thing, this weird thing. If we save, oops. We have a couple compilation errors we're going to have to solve. Here, let's see, it's saying that ReaderType does not take type parameters. We're trying to call apply here. That's what we're trying to do, right? We're trying to call the apply method of the case class. We got rid of the case class, so there is no apply method anymore. So we're going to have to add back an apply method. Oops. And remember what the apply method did? It just took the thing to run. It just took a function A to B. So we could implement it like this. So that's that one. Let's see what the next error is. Oh, that was the only error. Okay, so our object now works fine. We've we can still use reader in the same exact way we did before. I really dislike this one bug with Sublime. There we go. Nope. There we go. So we can go in the console. Right? We could say reader string int dot length. And to uppercase. Not sure what I did wrong there. That's a weird one. That's a strange error. It basically is thinking that it's getting confused between the reference to the companion object type, the type of this thing, and the reader type alias here. I'm not sure why we'd be getting that if the first one worked. It seems very strange to me. But anyway, we can use these in the same way. So let's just use the first one, for example. Here we can call hello or run with hello. We get the string length 5. Let's try just creating an increment. Yeah, no, same problem. Yeah, the REPL's confused for some reason. Some strange import reason, or the fact that this isn't a separate file. Maybe there's something weird that it's not liking. But anyway, once we fix that, then we can use this exactly the way we used it before. And we don't have this duplication that we had here. By the time we add a full suite of methods to our data type here, we probably have a few dozen. So while if we only had map, flat map, and then in compose, the duplication perhaps wasn't that unbearable. By the time we added everything we wanted, the duplication actually gets pretty bad. So anyway, this idea of representing or using a transformer to represent the non-transformed monad is pretty powerful, thanks to the, it's all thanks to the ID type constructor. And it's kind of neat, if you start with the, you take one of these methods, take an easier one like map, and if you go back to ReaderT, and say well, this is what the reader version of map looked like, and this is what the ReaderT version of map looks like. But then take the ReaderT version and start inlining the definitions from the ID monad. So you come back here and say well, this is what pure and flat map looks like for ID. Right? And if this is what pure and flat map looks like, then you can imagine what map looks like. We got it for free. We didn't have to write it, right? Our base class provided it to us. But remember what map looks like. We'd have this signature, right? An ID of A, a function from A to B, returns an ID of B. And effectively, the way this gets implemented, thanks to the base class, is flat map, FA, F, and then pure. And so anyway, if we start plugging all this together, if we take, we start here and say, okay, well, we're calling map on F, but map on F is really this, right? So let's put that in. And so you substitute all that and say that makes this into a flat map. And inside of here we get an and. Inside of here we get an and then pure, which this is really, of course, f.pure at this point. And you keep substituting, right? Like, so for example, let's do pure. Here's f.pure, but on the ID type constructor, what's pure? Well, pure is just the identity function. It's returning what's ever there. So we could replace f.pure with and then identity. And of course, like, anything and then identity is the same as anything, so we can just delete this. And now we're left with just flat map. And then so then we substitute flat map, right? And say, okay, well, given that, what does flat map look like? Well, flat map is really just FFA. So this whole line gets condensed into just F. Right? Just ends up looking like that. Now compare this signature or this implementation of ReaderT's map method with this one that we started with. Let's avoid point-free syntax. Let's write this up above in the closure syntax. We're just going to leave it the same. We're just going to use closure syntax, right? So we could start by saying, well, we're just going to introduce our type parameter, our value parameter A, and we'll just apply it to the overall expression. But then let's simplify that. Let's get rid of the function composition. We'll just distribute this application inside of here. And by doing that, what we end up with is run A, and then we're going to call F on the result of that. So now look at what this looks like here to what this looks like here. And you can see they're identical. Except that, one's a ReaderT and one's a reader. But, using just pure symbolic, algebraic substitution, we're able to show that, we're able to prove, quite literally prove, that our map function from ReaderT is absolutely equivalent to our map function from reader. Okay, and I think that's all I have for today. Any questions? Looks like there's one or two. Okay, so one of the questions was, can we compare reader to the state monad? So yeah, let's look at reader. Reader always just is a wrapper for A to B. It's a function, it's the monad for function application. But another more useful way or semantic way of describing what it does is that it lets us abstract over a dependency, right? An input parameter R, like this environment parameter that we use down here. Some dependency we have on something, we want to kind of be able to ignore it and compose all of these values together and then later apply that input parameter. That's sort of the point of the reader monad. And the reader monad, despite the examples in the REPL today, really can make code much, much, much cleaner if you have a lot of dependencies on a given value. Okay, but look, at the heart of it, it's just a function from A to B. Remember the state monad is also, a data type that has two type parameters. We typically call them S and A. It also wraps a function, but the function signature is a little different. Rather than just being a function from like S to A, or in the case of here, A to B, it's this shape, S to S comma A. Or like, let's say, let's just replace the type params with ones that use the same names as reader, so we can actually see the differences better. That's how state would compare to reader. So while reader is a function from A to B, state not only outputs a B for each A that's in, but it also outputs a new A. And the big difference here is that in flat map, right down here when we implemented flat map on reader, we saw that both the initial value run, this run here, this dot run, as well as the result of the run, the resulting, like the reader that came back from applying our function f, its run also needed an input A. They both needed that value, and we applied the same input value A to both of these two runs. So in a sense, that A was like broadcast into both runs. And if you have lots and lots and lots of values that you're flat mapping together, lots of readers, let's say you've got like a really big tree of reader calls, when you eventually run it, that single input parameter A is passed to every single reader in your entire tree. That's great for expressing dependencies, right? Like typical dependency injection, that's what reader does. But for state, that's not true. For state, state models like this dependency. Each step in the flat map, there's a dependency that says this particular step, I'm going to give you this input parameter A, and you're going to give me back a different A as output, and then I'm going to feed that output into the input of the next one. So like even though you'll see something similar here, where you've got two runs inside a flat map. The first run is going to start with your initial input parameter A, and the second run is going to be fed the output of this first one. So anyway, that's sort of the characterization there. The other question was, what's the equivalent of reader in Scala Z? So here we have Scala Z at the REPL. And the answer is that it's just reader. So like len. Oops. Right, so this is just Scala Z. Nothing fancy here. The examples that we did today all work. There's some details, or there's some conveniences about the Scala Z reader. So for example, you don't have to call .run. You can just apply it directly. And you can even see that like when I'm using reader and I don't annotate my result type here, the compiler infers like this identity type constructor. But if I was to say like val, length of type int equals len.run of hello, we have an int. So you can also see this hint on the right-hand side that Scala Z implements reader in the same way that we did. It's using a transformer. In Scala Z, it's not called ReaderT, it's called Kleisli, and it's this name comes from a certain concept in category theory as it relates to like free algebras over categories. But in category theory, it's named after a mathematician named Heinrich Kleisli. And so anyway, in Scala Z, they chose the category theory name for this concept. But like this type that you see in Scala Z is exactly ReaderT from today. And in fact, you can see if you look at Scala Z how many methods you can define on this data type. These are just the direct methods. These aren't even the type class instances. Here is where you start getting to type class instances, and it's just page after page after page. This is a very, very, very general data type, very useful data type. You can also see here, if you look at their code, like map, for instance, looks extremely similar to the map that we wrote. Right? Like this is the callback form of creating a ReaderT. You can see run A here is inlined with call to map of the function over it, as well as like flat map here you can see is exactly the same as our, the one we wrote. They're using the Haskell bind method, but it's the same thing. It's just an alias for flat map. You can also see that, I said we hadn't talked too much yet about like the flat map type class. Well, the flat map type class is equivalent to the bind type class from Scala Z. And you can see here that they didn't define flat map to take a monad, they defined it to take a bind instance. We saw the same thing in our code, right? That we didn't really need a full monad. We were able to get it to compile with just a flat map.